Hello friends, today we start with the new subtopic of the chapter linked list, that is singly linked list. Now, in the previous lecture, we already discussed what is linked list in detail. Okay, if you want the detailed description, detailed understanding of what is linked list, you can refer my previous video on introduction to linked list. In that, I am systematically explain what is the use, or what we can say, what is the importance of a linked list over the techniques previous two data structures that we are using to store the data inside the data structure. Now today we are focusing on singly linked list. It is the very primitive and basic type of a data structure, in that we are storing the data inside the singly linked list, but we are storing in a more systematic manner than the previous data structure. Like here, we are storing the data at the beginning, in the middle, at the end, and in the similar manner, we are deleting from the beginning, we are deleting from the middle, we are deleting from the end. So, it is a systematic insertion and deletion technique inside the singly linked list. With the help of linked list, we are creating the node. We know that. We are creating the node. In the node consists of the data and the address of the next element which we want to point. Okay. So this is all about the linked list. You just refer my previous video, then you clear the idea regarding the linked list. Now today we are focusing on singly linked list. Singly linked list is the simplest type of a linked list. I just told you that it is a simplest and the primitive type of linked list, in which every node contains some data. Okay, as the linked list contains the node, and the node it contains the data and a pointer to the next node of the same data type, and the pointer to the next node of the same data type, means whatever the data type that you are using for the element, same data type are using to store the data. Okay, and pointer points to the address of the next element which we want next to the previous element. Okay, so this is the systematic pattern. Now, in according to, by focusing on the figure, you can again more understand the concept of singly linked list. So we discussed this figure 6.7 in the previous lecture. What is start? Start always store the address of first element, then it moves on, first stores the address of second element, and so on. They are connecting with each other. So this is the simplest form of a singly linked list. Now next is, yes, for traversing the linked list, we also make the use of another pointer variable. So pointer variable is ptr. Now from onwards, for every step, algorithm is there. For every step, to insert the data at the beginning, to insert at the middle, to insert at the end. So after completion of this videos on different unit of the data structure, I am focusing on systematically explaining each and every algorithm which helps to understand, or which helps to write a systematic program. Okay, means once you understand the concept, now in this video you just focus on understanding the concept and try to write the algorithm of your own. And after that, once you understand the concept, just pick it out, the important factors. Now how you are doing that, That I will explain you one by one. Okay, just concentrate. Now here, see, PTR. PTR is the one important concept that we are writing when we are writing the algorithm. Now it is one of the pointer variable which points to the star. So whenever we writing the algorithm, we can write in the step one which whatever the step one we are included over here in such a manner we can write. Now see here, initialize a set pointer is equal to star. So PTR, set PTR. So we are not writing a complete pointer. So we are writing, in spite of that, we are writing PTR is equal to star. So that star points to the first element, right? Because we have to point element, then and then only we can store the data. So we are using pointer variable PTR which points to the node that is currently being processed. The algorithm to traverse a linked list is shown in the figure. Now I'm explaining the algorithm one by one. Now in this algorithm, first we initialize with address of star, address of start. Now pointer points to the first row, okay, of the linked list, as we are using start pointer. Then in a step 2, we are using a while loop which completes. Now here we are using the while loop, and what we are writing, repeat step 3 and step 4. For that we are using till. In the while loop we are providing the condition that pointer is not equal to null. So we are not getting the null up to that point. The pointer is incremented till we are not getting the null value. Okay, so pointer is repeated, and for that we have to repeat the step number 4 and step number 5. Okay, now we are applying the process. We are pointing to the data. Okay, and as we pointing to data, we got the address. Again the pointer pointing to the next data by using the pointer. These steps are going on till we're not getting the null. Okay, so in step 2 what we are doing, a while loop is executed which is repeated till pointer processes the last node, right? That is until it encounters null. In step 3 we apply the process. For example, here we are, for example, consider trend to the current node, that is the node pointed by pointer. In the step 4 we move to the next node by making the pointer variable point to the node whose address stored in the next field. Now see here, this is very simple algorithm. This is the first algorithm that we are writing for visiting each and every node in a simple manner. For visiting each and every node, we are using this algorithm. In the algorithm, we are setting the pointer to the start, because from the start, we what we can say, we are initializing our process of searching the node. That's why we write as a initialize set ptr is equal to start. Now we are using one loop, so that till we are not getting the null, the process is repeated, and with the help of that we are traversing each and every node. Okay, so to traverse each and every node, your ptr tends to data, your ptr all the time points to the data, and then this ptr is equal to ptr tends to next, means ptr is equal to ptr points to next, so that it points to the next node, and this procedure continues till we're not getting the null. As we get the null, this while loop breaks and we are going to the end of the loop. Okay, so this is the systematic procedure to visit each and every node. So this figure also explains algorithm for traversing a linked list. Now this is the simple explanation This is the simple explanation of the previous algorithm that we have starts. Okay, so what is that? I just read all the steps one by one. You just concentrate. In this algorithm, we first initialize the PTR with the address of star. So now PTR points to first node of the linked list. Then in the step 2, a while loop is executed, which is repeated till PTR processes the last node. That is, until it encounters null. In step 3, we apply the process to the current node, that is the node pointed by PTR. In step 4, we move to the next node by making the PTR variable point to the node whose address stored in the next field. Okay, so this is the explanation, or you can write in your own way once you understand the concept. This is the my way to explain you the concept. Once you understand the concept, you make a habit of writing of your own. Now, next is, now in this complete figure, we try to find some node. Okay, this is the simple part. We are systematically again studying a different cases. Now here, suppose consider the linked list as shown in this figure. If we have val is equal to 4, value is equal to 4, element is equal to 4, then how of the algorithm can be explained as shown in the figure. Okay, so by considering this complete figure, just understand each and every concept and try to write the algorithm. Now see here, by considering first part, right? So in this, PTR is points to the first node, which is having data is equal to 1. Okay, here PTR tends to data is equal to 1. Since PTR tends to data is not equal to 4, as we want to found the 4, means the node containing data is equal to 4. So it is not equal to 4, then we move to the next node, right? Then move to the next step. Now here PTR is equal tends to data is equal to 7. Now since again PTR tends to data not equal to 4, we move to the next node. Third step. Here PTR tends to data is equal to 3. Since data is not equal to 4, we move to the next node. And the last step, here PTR tends to data is equal to 4. Now condition is true. Okay. Now whenever the condition is true, here PTR tends to data is equal to 4. Since PTR tends to data is equal to 4, POS is equal to PTR, means we are pointing to the value that we want. So the POS now stores the address of the node that contains the value of that particular node, that contains the value, the val of the particular node. Okay, so we are stick to that position now. Why we are stick to that position? Because we want the element 4 and now we got that particular node. So that's why the POS is pointing to the address of that particular node, and we stop our searches as we got the value 4. In the previous figure, in the previous algorithm, what we are using, val is not equal to null. So in that null, in spite of null, just write is equal to 4. Val is not equal to 4. And once we get the 4, the loop is terminated. Okay, so this is all about a simple introduction of singly linked list. Now the next subtopic of singly linked list is inserting a new node in a linked list. Now from here we are inserting a new node by considering different cases, right? Now, in this section, we will see how a new node is added into an already existing linked list. Means we already have one linked list containing 4 to 5 elements. Now, here we are in a position to understand the concept, that's why we are considering less than 10 elements. We will take up 4 cases and then see how insertion is done in each case. Now here each case is very important to understand the concept of insertion at the beginning, insertion at the end, insertion at the given node, and inserted before a given node. So why I am repeating this? Because once you understand from the singly linked list, you can understand for the doubly linked list very easily. So this is very important and basic and very simple to understand the 4 cases of the linked list. Now case 1 is the new node is inserted at the beginning. Case 2 is the new node is inserted at the end. Case 3 is the new node is inserted after a given node. Case 4 is the new node is inserted before a given node. Okay, so I'm not explaining this, I'm explaining with the help of different cases, okay, so that you can understand it. Now the first case is the new node is inserted at the beginning. So let's focus on this. This is the pattern of understanding to inserting a node at the beginning of a linked list. Now this is the figure 6.12. This figure explains how we are inserting the node at the beginning of the linked list. Now suppose we want to add a new node with data 9. There is one node with data 9 and add it as the first node of the list. Now we are adding it at the beginning of the list. Now we have a sample of a linked list with us. The sample linked list contains 1, 7, 3, 4, 2, 6, 5. Now this total are 7 nodes with respective data and address. At end we have X means null. So at the null we have stop our search. Now at this position we want to insert a new node with the data 9. Now allocate memory for the new node and initialize its data part to 9. Okay. Now this is the new node 9 where we just want to allocate at the beginning. Now if we are considering the algorithm, now how we are writing the algorithm for this? So first of all, we have to consider or we have to check whether available space for the linked list is completely full or not. So before start with actual adding a new node, you first have to check for the overflow condition. Okay, so at the beginning in the step 1 you have to mention the algorithm regarding the overflow condition. Means what we have to write, avail is equal to null, then write overflow. Okay, means available memory whatever allocated is equal to null, means it is already full, so write overflow over there. And if such condition is not satisfied or if such condition is false, then we are allocating, then we are considering, or then we are having a chance to allocate memory for the new node. Okay, so for this allocation of a memory, there are some functions are available in the C programming, that alloc function, malloc function, to dynamically allocate the memory for particular node. Just remember that concept. So with the help of that, you can allocate the memory for new node. But here you have to first check for the overflow condition. So at this stage, you can practically implement the overflow and underflow conditions. Okay, so before start to write any program directly, focus on what are the variable parameters that we have to consider before writing any algorithm. Okay, so this is one kind of a parameter that we have to think first, that such a type of a space issue is there. If not, first of all we have to check, and then we are allocating or set a new node is equal to the available memory location. Okay, so in such a manner you can write the algorithm. Now we are having a new node, that is 9. Now add the new node at the first node of the list by making the next part of the new node contain the address of the start. Now see here, we already know, or up till now we are studying that start pointing to the first node, start pointing to the first node, start stores the data of first node. Now here we are in a position to allocate the memory for the new node which containing data 9. So whatever the next part of that node 9 which contains the data 9, now they are pointing to the start. Okay, right, and now make a start to point to the first node of the list. So in the next step, as you observe, now the start is 9, because what is the rule, that start always pointing to the first node and it having the address of the next node. So हमारा start, whatever our start is there, that is shift to 9 as it is the first node. So this is the systematically insertion of a new node in a at the beginning of the singly linked list. As we discussed in the previous linked list, that how to insert the new element at the beginning, at the position pivot, in the middle, or we can say in the middle, and at the end, by study 4 different cases. In the same way, in this video, we are discussing that how to delete an element from the given linked list. So, as we comparing to insert and the delete is more simple than insert any element inside the linked list. Now, before start with the today's topic, again I want to explaining the use of underflow and overflow. So, as we are having a total linked list with the different elements, and the next, that is the pointer points to the next node, in that case, in the insertion case, we are checking all the time which condition, overflow condition, so that if the overflow condition is satisfied, there is no chance to insert any new element. So in the similar manner, here we are checking that we are checking in the case of a delete, that whether the given linked list is completely vacant or not. So we are checking for what, underflow condition, because here we are checking, or here we are deleting the element. So as we are studied it previous with the previous data structure also, that before deleting an element we check for underflow condition, here also before deleting an element from a linked list we again check for the underflow condition. So before start writing algorithm, first in the step 1 you have to check for the underflow condition. Now we start deleting a node from the linked list. So in this section we will discuss how a node is deleted from an already existing linked list. We will consider three cases over here and then see how deletion is done in each case. Now case 1, case 2 and case 3. So what is case 1? The first node is deleted. The case 2 is the last node is deleted. And the case 3 is the node after a given node is deleted. Okay. So remember that in this case, while writing the algorithm, first we check for the underflow condition. So first we are focusing on deleting the first node from a linked list. Now there is one figure in the next slide, that is figure 6.20. When we want to delete a node from the beginning of the list, then the following changes will be done in the linked list. Now observe the linked list. It is very important and very simple. See, we are using a simple linked list, that is 1, 7, 3, 4, 2, 6, 5. All the elements are there with a specific pointer points to the next node so that we can move to the next node. And here we are using a start node to point it to the next node. Make start to point to the next node in the sequence. Means what we are doing, that we are providing the start pointer, we are providing start to point to the next node in the sequence. So we are giving start to that node itself. So if we want to consider the algorithm in this case, if you want to discuss the algorithm, so in which manner we are writing the algorithm, see here, just understand that is set start is equal to start which tends to next, means start points to the next element address. Start point to the next element address means automatically the start pointer which points to the first node is moved to the next node. So here start which is point to the first node, that is 1, is moved automatically to the second node containing 7, and now it points to the next node. Now it points to the next node. Okay, understand? So the 7 becomes the first node of your linked list. Why this has happened? Because you are setting start is equal to start tends to next node. First we are setting a pointer to the start, that is ptr is equal to start. Now we set start is equal to start, and that start pointing to the next, pointing to the address of the next element. So automatically start pointing to the next element. So automatically first node is deleted. So there is no importance of a first element. First we are setting pointer is equal to start, and then we are setting that start is equal to start which points to the next, the address of the next element. So it automatically shift this pointer to the second node of the linked list, and the first node is deleted. So in this manner, in a very simple manner, we are deleting the first node from the linked list. Now next, deleting the last node from the linked list. Now in which manner we are doing this? Okay, now consider the figure 6.22. Suppose we want to delete the last node from the linked list. The following changes that we have to observe in the linked list. Now see, this is a complete linked list. Here we have to consider the pre-pointer, because pre-pointer always points to the previous node of the pointer. Okay, so that it is very helpful to insert the new node whenever we want. Wherever we want, we can insert the new node with the help of this pre-pointer. That's why we are using three pointer, that is start pre-pointer and the normal pointer. That pre-pointer and pointer moving one by one, means they are moving with one by one, they are moving throughout the single linked list, one after other, like in this manner. Consider the linked list in a figure 6.22. Suppose we want to delete the last node from the linked list, then the following changes will be done in the linked list. Now we are starting with the first node, where it is 1, then 7, then 3, 4, 2, 6 and 5. These are all nodes. Now we are deleting the last one. Take a pointer variable ptr and pre-ptr which initially points to the start. Okay, then original actual procedure starts. Move pointer and pre-pointer such that next part of the pointer is equal to null. We are searching the node in such a manner that the next part of the pointer is equal to null. Okay, so so for that purpose for that purpose we are searching for the pre-pointer and the actual pointer which points to the null. And as our searches ends as our search ends now, as we are comparing or as we are considering the part of an algorithm, right? So in which manner we are writing? Again we are using the condition, that is if pointer tends to next is not equal to null, then up till now, until we have to search, until we not get next is not equal to null, we have to search for the null. And once we get the null, we just free that particular pointer. Once we get the null, we just free that particular pointer. Set the next part of the pre-pointer node to null. Once we get that particular pointer, we just free that pointer and use that and setting our pre-pointer as a to the null, so that that particular pointer is deleted, because we are our condition is true and we are free the space which is provided to that particular node, so that node is automatically deleted. Okay, and we are setting the next part of the pre-pointer to the null. So in this manner we can also delete the data from the last. Understand? Once we get the null, we are setting the condition, that is search till we are not getting the null. Pointer is not equal to null. Once we getting the null, condition is true, then we are setting pre-pointers is equal to null. Pre-pointer element. Here pre-pointer element is 6. So we are setting pre-pointer element is equal to null. So whatever the pointer which you are currently pointing, that automatically deleted. So this is all about deleting the last node from the linked list. Now next is deleting the node after a given node in the linked list. Okay, so for given node, again we are using both the pointer, that is pre-pointer and the normal pointer. Now here what is the procedure, that we are considering the figure 6.24, and suppose we want to delete the node that succeeds the node which contains the data value 4, and then following changes will be done in the linked list. So succeeding the 4, we are deleting that particular element. So first we are observing the normal linked list, that is start, then all the nodes are there. Then we are setting three pointer, that is start, pre-pointer and the normal pointer. We are focusing on the node which contains the 4 data as a 4. Now move the pre-pointer and the pointer such that pre-pointer points to the node containing value and pointer points to the succeeding node. So observe that first is the start pointer, then pre-pointer and the normal pointer. Now in the next step they are moving, they are searching for 4, that's why they are moving. From 7 they are moving to 3. Now from 3 they are moving to 4. Now they got the actual pointer that they wants to delete. So no, 4 is not deleted. After 4, whatever the node, that particular node is deleted. So after 4, the node is 2. Okay, the node which is containing 2. That particular that particular node, sorry, that particular node we wants to delete. This particular node we wants to delete, right? So what is the procedure then? Now once we get, now in the step 3, that is start, then now at this position our pointer is at, pre-pointer is at 4, normal pointer is at 2. Set the next part of the pre-pointer so that it points to the next part of the pointer. Understand? So after the this step you can understand, at the fourth step what we are doing, the next part of the pre-pointer pointing to the next part of the pointer. Pointing to the next part of the pointer means pointing to the next part of 2. So next part of 2 is 6. So 4 is directly pointing to 6. So the node which is succeeding to 4 is deleted. So the node which is succeeding to node 4 is deleted. So it is all about the game of a pointer. As you understand the game of a pointer, in the previous case we are pointing the pointer to the null so that the node which is at the last is deleted. Okay, now here we are pointing the next of the 4 to the next node, not the succeeding node, to the next node, that is 6, to the next part of the pointer, to the next node of the pointer that we are pointing, to the next part of the pointer. The next part of the pointer is 2. So the the next part of the 2 is 6. So it directly points to the 6 and 2 is deleted. Okay, so once again you have to go through all the steps slowly, understand it and form an algorithm based on that, so you just clear the concepts. Okay, so this is all about deleting the node after a given node in a linked list.